Today I will talk about different types of Diels-Alder reactions and some important examples that falls under the category of different Diels-Alder reactions. I will talk about them. So these are very important for CSIR-NET and conventional BSc and MSc pericyclic reactions, which you may find in the exam papers. Okay, so as I said in my previous lectures, that in the branch of pericyclic reactions, it accommodates cycloaddition, electrocyclic, sigmatropic, group transfer, and cheletropic reactions. And as we are dealing with cycloaddition reaction in major, so in this third lecture of this lecture series of pericyclic reactions, I will talk about different types of pericyclic reactions, and at the end I will also talk about some organic bioactive molecules synthesis by means of this Diels-Alder reaction and also photoenolization reaction. So in the first, the major types should be the intramolecular Diels-Alder reaction, Hetero-Diels-Alder reaction, and inverse electron demand Diels-Alder reaction. So we will gradually come to both or all the types of Diels-Alder reaction, and we will see the examples of those. To start with, the intramolecular Diels-Alder reaction, sometimes abbreviated as IMDA. Now this can be of two types. I will come to the second one, type 2, in the next slide, but the first one can be the type 1 IMDA, where the dienophile is attached to C1 atom of the diene. Okay, and definitely that will result in the formation of fused bicyclic systems. Okay, now as here you can see in the example, let me bring the highlighter. Yes, so here you can see in the example that with the C1 atom of the diene, here this is the C1 of the diene. As with this, the substitution takes place if the dienophile is attached, and eventually that will lead to the formation of a fused bicyclic system. Now in that case, for intramolecular Diels-Alder reaction, it works best when it forms 5 or 6 membered rings. Okay, so in that purpose, these are very useful reaction for the synthesis of 5 and 6 membered rings, especially the carbocycles. Next, the type 2 IMDA. In that case, the dienophile is attached to the C2 atom of the diene. Okay, and this generally results in the formation of bridged bicyclic system, and it provided that the ring formed other than 6 membered should be minimum 7 membered ring. Okay, this comes, or we have to account for the strain of the ring that will formed by means of this type 2 IMDA protocol. So this is, as you can see here again, that this is the dienophile is attached with the C2 atom of the diene, and eventually it will lead to a bridged, here you can see the bridged bicyclic system, and by means of this type 2 IMDA reaction. Now we will see some examples of type 1 IMDA and type 2 IMDA reactions. First, the examples of type 1. Here you can see a couple of examples where the diene at the C1 atom, from the C1 center or C1 point, the dienophile is attached with the diene. Okay, so as I said, that it will lead to the formation of bridged formation of bicyclic compounds. So this is a bicyclic compound, fused bicyclic compound, and usually preferred 5 or 6 membered cycles. Okay, here one more thing to say, that when we talk about the preservation of the stereochemistry or of the substituents in the dienophile, it is substituted normally, preserved normally in the Diels-Alder reaction, and here the intramolecular Diels-Alder reaction is no exception. Here you can see that this hydrogen atom and this CO2 Me group, they are cis fashion in the dienophile, and eventually on proceeding after hitting the compound, it will form the fused bicyclic system, and therein also the cis geometry or cis relationship of the substituents in the dienophile is preserved. Okay, so this is one important point that we need to remember when answer the questions in the competitive exams or exam papers. Again, this is another example where the dienophile is attached with the C1 point. You can see this is the C1 point here, and it forms a 6,6 fused bicyclic carbocycle system. And this is another example for this one. We will see a couple of more a little bit complicated system leading to some more stereo centers or stereogenic center in the end, which are building blocks of some natural products as well, some complex molecules. Here also you can see another one where the diene is substituted at one C1 atom, and the dienophile is flanked from the C1 atom of the diene, and eventually leading to the formation of fused bicyclic systems. Okay, and this is another example you can see in the right hand side, that that is the similar demonstration of the IMDA type 1 example. We will see another one here. You see, this is another classical example for this IMDA reaction. You will find this very often in different books, where you can see that first, upon heating, this 4-member cyclobutane ring, which is fused with the aryl ring, that the electrocyclic ring opening takes place in that case upon heating, eventually leading to the formation of a cis diene system, which now is eligible for the intramolecular Diels-Alder reaction, and the dienophile is flanked with the C1 atom of the diene, and thereby giving us a tetracyclic ring structure having several chiral centers within the molecule. So these are very important in sense of biological activity. So we can access biologically active molecules while incorporating intramolecular Diels-Alder reaction as a tool. Next, we will see some examples of type 2 intramolecular Diels-Alder reaction, where, as you can see, the dienophile will be attached with the C2 center of the diene system. We will have a couple of examples over here, and definitely at the end we can have this bridged bicyclic system as the major product, as I have said earlier. So here are several examples where you can see, according to the design, molecular design, to get the desired product, it can be arranged in such a way where the dienophile and diene are oriented in the form of intramolecular Diels-Alder reaction of type 2 category, and upon heating that can eventually end up with the product formation. This is again another example for similar kind of reaction, giving the bridged bicyclic systems, which are the major product of type 2 IMDA reactions. Another one, so by means of BF3 iterate Lewis acid catalysis, and we can have these bicyclic ring structures of several ring sizes. Next, we will talk about the Hetero-Diels-Alder reaction. As I said, the second category of the Diels-Alder reaction, where by name you can understand that the heteroatom should be the part of the diene and the dienophile. So there are two possible ways of having the Hetero-Diels-Alder reactions. Either the diene is heterodiene or the dienophile is heterodienophile. That means you can have heteroatoms in either cases. First, we will talk about the heterodiene system. Okay, so that means the heteroatom is the part of the diene in that cases. So we will see a couple of examples here. First this one, again another one, this. So we can see that with these examples, you see this is the diene system, where oxygen being the part of the diene, the heteroatom, and we have a dienophile. This is also constituting in a cyclic ring structure having a heteroatom, but that doesn't make sense because the dienophile that is here doesn't contain any heteroatom. So here only the diene system having a heteroatom. So the reaction proceeds usually to form this bicyclic ring structure, fused bicyclic ring structure, with the substituents intact and the stereochemistry as I have said in earlier slides. Another example where this diene system incorporating oxygen atom in the diene reacts with the ethyl vinyl ether, the dienophile, and to give a cyclic oxygen containing heterocyclic compound with different functional groups, which are uh, potent for further functionalization into another functional groups. So these molecules are very important as well in terms of functionalization and to get other complex molecules. So the second type that we want to talk is the heterodienophile. That means the heteroatom will be part of the dienophile in these cases. Here you can see the three examples are given in all the cases. This is the, carefully have a look in the dienophile. Here this is the imine. So nitrogen being the part of the dienophile, here the carbonyl group, oxygen being the part of the dienophile, here nitrogen again, another imine, and the diene system is normal with the carbon skeleton. Okay, but having different substitution, that's upon the design of the reaction, and thereby giving the product, and definitely the product has to be heterocyclic molecules. So these are another advantage of Diels-Alder reactions, especially the Hetero-Diels-Alder reactions, because by that mean we are able to access several heterocyclic molecules by simple 4+2 cycloaddition reactions. Next, we will talk about the third type, the inverse electron demand Diels-Alder reaction. As the name goes, we can understand the normal, this will be inverse in sense of the electronic character of the normal Diels-Alder reactions. And usually what we had before in the Diels-Alder reaction, that the diene should be electron rich and dienophile should be electron poor. However, in inverse electron demand 4+2 Diels-Alder reaction, the diene is supposed to be the electron poor system and the dienophile is supposed to be the electron rich system. That means any electron withdrawing group in the diene part and any electron donating or releasing group in the dienophile part will enhance the rate of the reaction. Okay, so here is a simple demonstration of that kind of inverse electron demand reactions. There are many examples, and as you can see, the diene here is a part of a cyclic ring system, cyclic lactone, and having ester functional group attached as a substituent in the molecule, while we are having a vinylic ether system as the dienophile, where this is the electron rich system, the dienophile is electron rich, and diene is electron poor because of heteroatom in the ring structure. Usually this will go the traditional 4+2 cycloaddition reaction, giving this bicyclic ring structure. In the breached center, you can see that we can have the heteroatom containing system. So these are prone to decarboxylation. So as you can see here, the decarboxylation will lead to a cyclic system with ester substitution. However, the driving force of aromatization leading to the removal of alcohol molecule, as you can see that alcohol molecule can be removed and thereby giving a aromatic ester molecule as the product. So these are very important reactions, and in inverse electron demand reaction, especially if you have the lactone skeleton in the diene system, they are very prone for the decarboxylation, and further if there is possibility, then removal of alcohol molecule will lead to aromatic compound. We will have another example here with different dienophile and diene system. Here also the diene has another fused ring structure, aliphatic ring structure along with it, and also the lactone ring as a inherent part of the diene system. Then it reacts with the vinyl system here with the dimethoxy substitution, making it more reactive towards the diene, and the 4+2 cycloaddition reaction gives us the following product, which undergoes decarboxylation process followed by removal of the alcohol molecule, giving the desired aromatic ether molecule, while it is the aromatic ring is fused with another aliphatic ring structure. So these are a couple of examples of inverse electron demand reactions. I will show a couple of more which are very interesting and which are of recent trends. These two examples are very important. As you can see, the first example, this is itself a heterocyclic radical, ammonium ion radical, and we have a vinylene radical over here. Now, as you can see in the substitution pattern, that if the R1 and R2 of the dienophile system are electron releasing or donating group, then the reaction proceeds very quickly, and we can have the breached bicyclic product having heteroatom in the ring structure. So this heterocyclic structure, ammonium structure, quaternary nitrogen center. So we can have this in only 4 minutes at a 25 degrees centigrade temperature. That means a quite mild reaction condition. Okay. Now, depending on the other substituents here, especially if we go with this one where R1 is cyano and R2 is hydrogen atom, in that case the reaction takes severe time, that means a prolonged time and a higher temperature as well. So that means the more the dienophile will have electron donating group in the dienophile system, the reaction will be much visible and faster, giving to produce the product in a mild reaction conditions. So this is very important when we are talking about the inverse electron demand reactions, Diels-Alder reactions. Again, the second example of this diene system having a carbonyl group attached with that in the ring structure and substituted with 4 phenyl groups in the diene part. Okay, so heavily substituted diene system. Okay, so all the electron withdrawing groups are attached with the diene system, and we take the styrene molecule which have other substituents in the aromatic ring, and that can be, you can see here with the electron donating to, we can see here up to electron withdrawing groups as well. And in that case, the rate of the reaction, you see how dramatically the rate of the reaction changes with the value of here with the rate constant. Here also, at the end of the reaction, you will have this bicyclic breached heterocyclic ring structure, and this is the beauty of the inverse electron demand reactions, which allows us to get the 4+2 cycloaddition product with reverse electronic character in the diene and dienophiles from the usual Diels-Alder reaction. Okay. Next, we will talk about estrone, the biologically active molecule, in fact a steroid itself, and this is basically a weak female sex hormone. So how we can access the estrone, and two other parts are estradiol and estradiol, and so estrone is a very important compound in that sense, and now we will see how we can access estrone by using the tool of Diels-Alder reaction. So first 2 steps can set the reaction up. Here first you can see here the cyclic enone system with alpha beta unsaturated carbonyl compound, the cyclic carbonyl compound, which undergoes reaction with the vinyl magnesium bromide and in presence of copper iodide and trimethyl chloride, giving a 1,4 addition product of vinyl silyl ether, as you can see over here. This is the silyl ether complex, and then it undergoes reaction with this dialkyne system having aliphatic Ci bond. So this Ci bond is eligible for undergoing the usual Heck reaction. Okay, so in presence of a base and in presence of THF, it undergoes the Heck reaction, and eventually you get the product and the 2-methylene group flanked with this cyclic structure. We get the dialkyne or diene system over here. Now this is beautifully set up for a Diels-Alder reaction, and we will see then in the next step that when trimethyl silyl substituted acetylene disubstituted acetylene compound in presence of cobalt carbonyl catalyst, they undergoes reaction. So this leads to this compound where this cyclobutane kind of ring, which is fused with the aromatic ring structure, and it produced like that. Now this, I have said before that this kind of ring structures are very prone towards the electrophilic ring opening, and at 170 degrees centigrade in that happens actually, and we get this diene system from this cyclic structure. So this sets up very well, and already you have the flanked vinylene group with here this vinyl group over here. So this gives the opportunity for the 4+2 addition reaction, again the Diels-Alder reaction, to go for the cyclization process. As you can see here, the tetracyclic compound is obtained. Now, to get the estrone from this tetracyclic compound, the trimethylsilyl groups need to be removed, and you have to install a hydroxy group in place so that you get the estrone molecule. And that step is done in 2 steps. First, the trifluoroacetic acid in carbon tetrachloride at very low temperature, it reacts for desilylation, and followed by oxidation with the lead tetraacetate salts with trifluorotetraacetate salt compound, which is a oxidizing agent, and then it gives estrone as the major product. So we realize how Diels-Alder reaction can be used as a simple tool or in one of the steps to access biologically active compounds. Next, we will see some photochemical cycloaddition reactions of very importance. Like here, it can be the 2,2 cycloaddition, 2+2 cycloaddition reaction. And you see the ethylene molecule can react with another alkyne, which is another alkene or olefin, the dienophile system as well. And so here, which is heavily substituted with carbonyl compounds, and the reaction undergoes in photoirradiation, giving this fused bicyclic ring structure. In the 4+4 cycloaddition reaction, 2 molecules of this anthracene molecule can react under photoirradiation, giving this the dimer kind of ring structure with the new CC bond forms over here. So specifically, this diene system will take part in the reaction, the pi4 system with pi4 system of another anthracene molecule, giving this product. 6+6 cycloaddition reactions are also possible with a cycloheptatrinone compound, and 2 molecules of those under photoirradiation in presence of acid gives another ring structures with 2 carbonyl compounds at the opposite side of each other to minimize the electronic repulsions, and giving us the compound like this. So we can understand that photochemical cycloaddition reactions are also possible, giving some complex molecules which are otherwise a bit difficult with other synthetic protocols to achieve. Okay, so another example of photoenolization, couple of examples have been shown over here. So the first one goes with this aromatic aldehyde compound, or aromatic carbonyl compound rather say, having a aliphatic chain over here, and under photoirradiation the carbonyl compound gets excited, and this photochemical reaction takes place, producing this diene system and also the enol over here. So this is a part of the diene as well. Now this diene is set up for a 4+2 cycloaddition reaction with dimethyl acetylene dicarboxylate, and then we will have this bicyclic ring structure, aromatic fused ring structure. Okay, followed by dehydration process leading to the aromatization, and eventually end up with a highly substituted naphthalene derivative. Okay, so this is a very good example of photoenolization reaction. There is another photo example of that, where you can change the dienophile system from this very linear dimethyl acetylene dicarboxylate to the cyclic one with the maleic anhydride. So this diene system with the enol system also reacting with this dienophile, the maleic anhydride, will end up with this tricyclic ring structure, and this kind of complex molecules is also possible to obtain by means of photoenolization reactions. So up to this today. Thank you very much for watching TG Chemistry. Keep watching. If you like the videos, don't forget to subscribe my channel, and also don't forget to press the bell icon to get the notification when I upload the next video. Thank you.